So the next topic in embedded system are the applications of the embedded system. So the applications are, it is used in consumer electronics, household appliances, home automation and security systems, automotive industry, telecom, computer peripherals, computer networking systems, healthcare, measurements and instrumentation, banking and retail, card readers, wearable devices, cloud computing and Internet of Things. Okay. So these are the important applications. So the next topic is elements of embedded system. So this is a structure of the different elements of the embedded system which consist of the system core or your heart of your embedded system, which may be the process such as field programmable gate array or application specific integrated circuit, digital signal processor or system on chip, microprocessor or microcontroller based system core. To the system core, you have your different input ports and output ports, memory, and the interfaces, communication interface, and other supporting integrated circuits and subsystems. Whereas your input ports, it is nothing but your sensors, such as examples are your keyboard, push button, switches, etc. Whereas your output ports, it is actuators, example is LED, LCD, piezoelectric buzzers, etc. Okay. So the memory, which consists of your actual code, and the control algorithms, configuration details, etc. Okay. So these are the major elements of your embedded system. The next topic is your difference between your microprocessor and microcontroller. So the microcontroller and microprocessor difference is that a microprocessor is a silicon chip representing CPU which is capable of performing both your arithmetic or logic operations according to the predefined set of instruction. But whereas in the case of microcontroller, it is a highly integrated chip that contains a CPU, scratchpad, RAM, special and general purpose register arrays, on-chip ROM, flash memory for program storage, timer and interrupt control units and dedicated I/O ports. Okay, these are some additional features of your microcontroller. Now, dependent microprocessor is a dependent unit. It requires combination of other chips like timers, programs and data memory chips, interrupt controllers, etc. for functioning, whereas in the case of microcontroller, it is self-contained unit and it does not require any external interrupt timer, UART for functioning, etc. Okay. Mostly general purpose in design and operation, microprocessor, whereas your microcontroller is always application oriented and domain specific. Microprocessor does not contain built-in I/O ports, whereas it contains microcontroller contains multiple built-in I/O ports. And the microprocessor is targeted for high-end market where performance is very important, whereas in the case of microcontroller, it is targeted for embedded market where the performance is not so critical. The last one is limited power savings options compared to the microcontroller. So whereas your microcontroller includes lots of power saving features. These are the main difference between your microcontroller and microprocessor. And the next is your difference between RISC and CISC. So what is meant by RISC? It stands for reduced instruction set computing, and CISC stands for complex instruction set computing. So the name itself gives you the meaning. Okay, RISC, lesser number of instructions are used, whereas in the CISC a greater number of instructions are used. So here you have orthogonal instruction set. What is meant by orthogonal instruction set? All instruction types can use all addressing modes. That is called as orthogonal instruction sets, whereas in this case of CISC, it is non-orthogonal instruction set. Then in the case of RISC, operations are performed on the registers only, and the only memory operations are load and store. But whereas in the case of CISC, operations are performed on registers or memory depending on the instruction. Okay. So in the case of RISC, programmer needs to write more code to execute a task since the instructions are simpler ones. Whereas in the case of CISC, instruction are like macros in C language, a programmer can achieve the desired functionality within a single instruction itself. RISC consists of single and fixed length instruction, whereas your CISC consists of variable length instruction. Then in the case of RISC, less silicon usage and pin count is required, whereas in the case of CISC, more silicon usage since more additional decoder logic is used to implement the complex instruction decoding. And the last difference is that RISC uses hardware architecture, whereas your CISC uses either hardware or von Neumann architecture. The last topic in your first section of your module 3 is your difference between your architecture, that is your Harvard architecture and your von Neumann architecture. The main difference lies in the fact that Harvard architecture uses a separate bus for instruction and data fetching. See here, here this will be your diagram of your Harvard architecture where it uses separate bus for your instruction and data fetching, whereas in the case of von Neumann architecture it uses a shared bus for instruction and data fetching. Okay, Harvard architecture, it is easy to pipeline, so high performance can be achieved, whereas in the case of von Neumann architecture, low performance compared to that of your Harvard. It is Harvard is high costly, it is von Neumann is cheaper. Harvard no memory alignment problems, but von Neumann allows self-modifying codes. And the main difference is that in the case of Harvard architecture, since data memory and program memory are stored physically in different locations, there is no chances for accidental corruption of program memory, where in the case of von Neumann, since it is shared, there are accidental corruption of program memory. So these are the main difference between your both the type of your architecture.